Hi, we're going to do worksheet 9 and review these solutions. That's the wave nature of light. Okay, so question 1 is light passing through a double slit arrangement is viewed on a distant screen. The interference pattern observed on the screen would have the widest spaced fringes for the case of... Well, okay, we know that for double slit interference, n lambda equals d sine theta. So we could say sine theta is n lambda over d. For small angles, the sine of theta is equal to theta. That's if you work in radians. So approximately theta equals n lambda over d. And what are we after? We are after wide spacing fringes. So if we want theta large, we would need a large lambda and a small d. So large lambda will be red light, and D slits close together. So red light and a small slit spacing C. That makes sense. Okay. Question 2. The colors in a rainbow are caused by, well, we discussed this in the slides. It's the dispersion as the light passes through. You see that the light comes through, and I mean it's dispersive, so the angle of refraction changes depending on the wavelength. So of all the choices, different amounts of absorption, no. Downward motion of the drops, no. Interaction of the light reflected from different raindrops, no. Different amounts of refraction for light of different colors by the water in the raindrops, yes. D. Water is dispersive. The speed of light in water depends upon the frequency. Okay. Question 3. A double slit experiment yields an interference pattern due to the path length difference from light traveling through one slit versus the other. Why does a single slit show a diffraction pattern? So a double slit is easy to understand. A single slit is a bit harder to understand. And I think I do have an illustration. We'll sort of jump ahead a bit here with solutions. And I did mention this with the slides. Yeah, you want to look here. This is my single slit interference. Now imagine that each point on the slit, again imagine this is a slit coming out and we're looking down upon the slit, but each point on the slit acts as a source of wavelets. Let's think, this is the one we probably want to look at. This is a single slit as well up here, so the diagram by the answer to question 6. Now you can see here we have one wavelength, so that is one wavelength longer than that. So you'd imagine we get constructive interference, but actually we get destructive interference in this case, because you see that one is a lambda difference, and that one is half lambda, so that one and that one destructively interfere. This one and this one destructively interfere, so we can sort of pair them off, and the net effect is when this condition is met, we get destructive interference and we get a dark fringe. So this is a kind of a bit weird, because this was the condition for a bright fringe with a double slit, but for the single slit this is the condition for destructive interference. But coming back to the question, which is a lot simpler than that, it's question 3, wasn't it? Why does a single slit show a diffraction pattern? Well, it's because the light coming from different parts of the slit interferes. Okay, and if we look at the possible answers, the wavelength of the light is shorter than the slit. No. Light passing through the slit interferes with the light that does not pass through. No. The single slit must have something in the middle of it. No. There is a path length difference from waves originating at different parts of the slit. D. So answer for 3 is D. Okay. If a thin film has a thickness that is a half a wavelength constructive interference, there's several of these, and then E is none of the above is always true. Now remember, we did mention when we were looking at the slides that when you get a reflection from a boundary, it can be inverted. So if we look at this, if we have this wave coming in, if the speed in this material is slower than this material, so if it's going into a denser medium, we'll say, then the reflected wave is flipped upside down. If it's going into a material where the speed is faster, the reflected wave comes the right way up. Again, I mentioned this before. This was in a video we observed. So because of this, really none of the above is always true, because it depends upon the media, right? It's the reflected wave. Are we going from a dense to a rare, or a rare to a dense material? Because we can get half a wavelength difference. So the answer for 4 is none of the above is always true for that reason. Okay. Question 5. Let's just scroll that up there. 2 coherent sources of radio waves, A and B, are 5 meters apart. So A and B, 5 meters apart. Each source emits radio waves with a wavelength of 6 meters. Consider only points along the line connecting these sources. Okay. At what distance from source A is the constructive interference between points A and B? Okay. At what distance is from source A is the destructive interference? Okay. So where would we get constructive and destructive? So what I'm going to do is to say that the distance from A will be R1 and the distance from B will be R2. So R1, R2. So I know then that R1 plus R2 has to be 5 meters, right? Because if R1 is 0, then the distance from B is 5 meters and so on. So that's how I'm going to define R1 and R2. R1 plus R2 is 5 meters. Now, the difference in the distance from the sources is R1 minus R2, right? So that's the difference in the distance from the sources. For constructive interference, I want the path length difference to be equal to an integer number of wavelengths. So I've got n lambda here, and n can be an integer like that, okay? What I can then do is just solve this simultaneously. I guess what I've done here is I've said R2 equals 5 minus R1, substituted it into this equation, and solved for R1, okay? Lambda, of course, is 6 meters. So let's figure where these are then. If I put n equals 0 here, I get R1 is 1/2 of 5, 2.5 meters. So there's a maximum there. And n equals 1, R1 is 5.50 meters. Well, the distance from R1 is 5.50. That's there, that's outside. So I'm not interested in that one because I want the points in between. And then if I put n equals minus 1, that comes out R1 is minus 1/2, and so that's outside. So between the points, I only have one point where they constructively interfere. For the destructive interference, let's have a look. It's basically the same idea, and we're going to do the same thing, only now the condition for destructive interference is this, that the path length must be either half a wavelength, 3/2 a wavelength, and so on. Okay, we solve the equation in a similar way, and then I've got n equals 0, n equals 1, n equals minus 1. And these are the 4 values, R1. So that is between the points, that is not between the points, that one is between the points. So we see we get 2 solutions where we get destructive interference, and we'll get destructive interference here at 4 meters and 1 meter between the points. And the n equal 1, get destructive interference over here, but we don't really care about that point. Which question are we on? That was 5. Question 6. You have been asked to measure the width of a slit in a piece of paper. Aha, it's a slit. A slit means it's single slit interference. You mount the paper 80 centimeters from a screen and illuminate it from behind with a laser light of given wavelength. You mark 2 of the intensity minima as shown in the figure and measure the distance between them to be 17.9 millimeters. What is the width of the slit? Okay. Well, if for single slit interference, we have the equation that n lambda equals d sine theta. That's for minima. Okay. What is the angle? Well, using a simple bit of trig, the angle theta is the d minimum over d screen. Well, the distance between the 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 distance from the center to the third minimum is 17.9 millimeters, but I have to divide that by 2 because the distance given is either side of the central point. Right, so hopefully you can appreciate that that is the distance from the center to the third minimum out. This is the distance of the screen, so a simple bit of trig gives me the angle. So there's the angle there, okay? This is a minimum, and if you count out, it's the first, second, third. It's the third minimum. So n lambda equals d sine theta, d equals n lambda over sine theta. N, it's the third order. I've got the wavelength, I've got the angle, and so I can see the distance, so the width of the slit will be 170 micrometers or microns. Okay, pretty small. Okay, question 7. Monochromatic light falls on a slit that is 2.40 times 10 to the minus 3 millimeters wide. Okay. If the angle between the first dark fringes on either side of the central maximum is 26 degrees, dark fringe to dark fringe, what is the wavelength of the light used? So again, this would be single slit, and the angle would be 13 degrees. First dark fringes either side, so I need to take half of 26, and it's the first dark fringes, so n equals 1. So I've got theta equals 13 degrees, n equals 1, and I want lambda. Okay, so let's write down the equation for single slit interference. N lambda equals d sine theta, lambda equals d sine theta, and so I've got my d, the slit width, I've got my angle. It must be 540 nanometers, right? So we can measure the wavelength of light using a single slit and a protractor, which is kind of pretty cool when you think about it. Okay, 8. Two polarizers are orientated at 50 degrees to one another. Unpolarized light falls on them. What fraction of the light intensity is transmitted? Okay, so we have unpolarized light. I don't have a diagram here, but the intensity, you'll recall that the intensity is I squared, the intensity is I cos squared theta, and that arises because the electric field, the component of the electric field goes through, but the intensity goes as the square. Now in this case, the intensity that will go through will be 1/2 of I0. Why is this like this? Well, because we have polarized light coming, unpolarized light, that's how much gets through the first polarizer. So that is the light going through the first polarizer. That we then have to do the cos squared theta. So hopefully you can see this. I've got I over I0 for the fraction of the original light. The half comes from the fact it has to go through one polarizer. We lose half the intensity there. And then we've got the cos squared theta term. So when I evaluate this, I get about 2/10 of the light will come through. Question 9, the last question. Water waves having parallel crests 4.9 centimeters apart pass through two openings 7.6 centimeter apart in a board. Aha, this is double slit interference, isn't it? Only now we're not talking about light, we're talking about water waves, but the same physics. At a point 3 meters beyond the board, at what angles relative to the straight through direction would there be little or no wave action? Okay, so if this is double slit interference, I know that the condition for destructive interference, I need half a wavelength difference. So this is my condition for destructive interference, because I want the points where there's little or no wave action. The wavelength is given, 4.9 centimeters, a distance from crest to crest, and the two slits are separated by a distance of 7.6 centimeters. Okay, this diagram shows us what's going on. Look, here's S1, here's S2. This is the separation distance. We've got lambda. This is for constructive interference, but we don't care about that. In this case, we want where there's no wave action, so we're looking at the destructive interference. And so we need this extra distance here to be half a wavelength, 3/2 of a wavelength, 5/2, and so on. Okay, so there's my equation for destructive interference. and what I want is the angle, so I can solve this for the angle. There we go. And then I start plugging in, the orders. For n equals 0, when I put 0 in here, I should have solved this more generally, I guess. But when I put 0 in, I get lambda over 2d, and 19 degrees. For n equals 1, I get 3 lambda over 2d, and I get 75 degrees. Now, interestingly, when I put n equals 2 in, and I solve this, I get the inverse sine of 1.61, which there's no solution to that. If you think about what a sine wave looks like, as you go with the angle, it goes like that, but it hits a maximum of 1 and a minimum of -1. So if I say the inverse sine of 1.61, that's nonsense. That isn't a solution. So we'd only find a minima at these two angles in here. Yeah, okay, a pretty short worksheet, and that's all there is to it. Yeah, have a go at it, make sure you understand, and I think that's it. A message from our sponsor.